the previous session we begin to present definition of LP spaces. Okay, fix a measure space X as mu and a positive number P. We begin this chapter by looking at the vector space of measurable functions such as f from X to F, such that this integral be finite. Okay, and then we see Holder and Minkowski inequalities, and finally we can define LP as a normed space. Okay, at the first, for Holder inequality, we define P norm of F. Suppose that X as mu is a measure space, P belongs to this interval, and F from X to F is a measurable function. Then the P norm of F is denoted by this, defined by this equality, P norm of F equal to this integral to the power of 1 divided by P. Okay, and infinity norm of F, which called essential supremum of F, is defined by this equality. Is equal to the infimum of all T, such that mu of this set equal to 0. Okay, and we see some example such as this. If consider counting measure on natural numbers, any sequence such as this have this P norm and this infinity norm. Okay, LP of mu. Suppose X as mu is a measure space and P belongs to this interval, then Lebesgue space LP mu, sometimes denoted by this completely, LP of X as mu. Okay, this measure space is defined to be the set of S measurable function F, such that this norm be finite. Okay, this norm or this integral. Okay, this integral or this infimum be finite. Please note that this P belongs to 0 up to infinity, so that this define P norm and infinity norm, or LP for P belong to this interval. Okay, dear students, do you have my voice? Wa alaikum assalam, Mr. Sajjad, do you have my voice? Okay, thank you very much. I am reviving some definition in the previous session. Okay, LP of mu. the set of all Lebesgue or S measurable functions f from x to f such that this norm be finite, denoted by LP of mu. For example, in natural number with counting measure, LP is the set of all sequences such as this, such that this P norm be finite, and at infinity is the set of all sequence such that the supremum is finite. We saw that LP of mu is a vector space. Suppose X as mu is a measure space and P belongs to this interval, then we have this inequality, and this equality. This shows that if f and g belong to LP, then f plus g belong to LP too. Okay? Because a direct consequence of this inequality is this. If, for example, f and g belong to LP of mu, then f plus g must be belong to LP of mu by this inequality, because f and g belong to LP of mu implies that these two norms, these two P norms are finite, this and this. Okay, so we see that this P norm is finite too, and this shows that this must be belong to LP of mu. Okay, by this inequality, if this and this be finite, this must be finite, and this equality shows that if f belong to for example, f belong to LP of mu and alpha belong to or field f, then alpha f must be belong to LP of mu, because the norm P of alpha f equal to this absolute value multiplied by, and this is finite, so that alpha f must be belong to LP of mu. Okay, this too shows that LP of mu is a vector space. LP of mu, by this definition, the set of all S measurable functions such that this P norm is finite, is a vector space. and we define dual exponent p prime for any p belonging to this interval 1 up to the infinity. The dual exponent of p is denoted by p prime and is the element of this interval such that we have this equality. Okay, these two fractions equal to 1. Example, 1 prime equal to infinity, because if we consider p equal to 1, is equal to 1, and so that 1 prime equal norm 1 of fh is less than or equal p norm of f and multiplied by p prime norm of h. This proof is easy and only you must apply Young inequality. Okay, for the cases p equal to 1 or infinity, this inequality is trivial, because for example, if we consider okay, if we consider p equal to 1, okay, if we consider p equal to 1, then p prime equal to infinity. Okay, and we know that this integral is, or this norm 1 of fh, okay, equal to this integral, and this is less than or equal this multiplied by this norm. It is very trivial because we know that absolute value of any function is less than or equal its essential subnorm. Okay? So that this integral is less than this integral, and this is a constant, so that it is equal to this norm multiplied by this integral, and this is norm 1. Okay, so that this is equal to this norm multiplied by this norm. And also, if p equal to infinity, then p prime equal to 1, and similarly we have this inequality. One norm is less than or equal. If norm, infinity norm multiplied by h1 norm. Okay, so that in the book, for proof, leaving the cases p equal to 1 or infinity as exercise. This is very trivial. In other cases, in this case, okay, first consider the special case where these two norms equal to 1. Then Young inequality tells us that we have this inequality. This is Young inequality. This inequality of x and the value of g of x. Okay, so that we have this ab is less than or equal a to the power of p divided by p plus b to the power of p prime divided by p prime. This holds for all x. So if we take integral in both sides of this inequality with respect to mu, we see that the integral of this less than or equal this integral. Let me write this. If h for this case p belong to 1 infinity, we see that if we consider a equal to this and b equal to this. Okay, this or h of x if x is less than or equal a to the power of p divided by p plus h of x to the power of p prime divided by p prime. This holds for any x in all set x. Now we can take integral, the integral of fh d mu is less than or equal this integral d mu plus this integral. Okay, and this is equal to this multiplied by the p norm to the power of p, because p norm is this by the power 1 divided by p. Okay, and plus this scalar multiplied by this norm p prime to the power of p prime, and all of this equal to 1, so that this is equal to this summation, and this summation equal to 1 by this assumption. Okay, both of this equal to 1, so that we have this equal to 1, and this 1 can be written as this multiplication. Okay, p prime, because both of this equal to 1, so that if we consider these two norms equal to 1, we have this inequality. The norm 1 of fs is less than or equal p norm of f multiplied by p prime norm of h prime of h. Okay, because this is equal to norm 1 of fh. Now if one of this equal to 0, sorry, if this equal to 0 or this, then we have this inequality. For example, if the p norm of f equal to 0, if the p norm of f equal to 0, then we see that this norm equal to 0, and this shows that this function must be 0 mu almost everywhere, and so that f equal to 0 mu almost everywhere, and this shows that fh equal to 0 mu almost everywhere, mu almost everywhere. If f equal to 0, this must be equal to 0, and so that this integral and so that this integral must be equal to 0. Okay, so that we have this equality. Zero is less than or equal 0. This 0 equal to this. And this 0 equal to this integral. Okay? Because we see that this is equal to 0 and we assume that this equal to 0. Similarly, if this norm equal to 0, then we have this inequality, because this is equal to 0 by our assumption that this is equal to 0 and this is equal to 0, this integral. Okay? Now, if these two norms are non-zero, okay, we have these two nodes equal to 1. Because this is equal to this and P, and this is equal to 1, and P prime norm of this equal to and this is equal to 1, 2. We use this equality, okay, consider alpha equal to this constant, okay, this constant or this constant, okay. So by the first step is that these two norms equal to 1, okay, these two norms equal to 1, because these two norms equal to 1. If, for example, we consider f1 equal to this and h1 equal to this, since P norm of f1 equal to P prime norm of h1 equal to 1, we have this integral f1 h1 d mu is less than or equal P norm of f1 multiplied by P prime norm of h1. Okay, but this is equal to f1 h1. This integral f1 h1 divided by this p norm and h p prime norm. Okay, and this is equal to this scalar multiplied by this integral. Let me write this. By this norm. Okay, P H P prime, and this integral of this norm 1. Sorry, this is f, not f1. Okay, f and h. Okay, and in this side this is equal to norm p norm of this. Or more simpler, is equal to 1, because both of this equal to 1. Okay, and so we see that if we multiply both sides of this inequality by this, we see that this norm is less than or equal this p norm multiplied by this p prime norm, and we prove this inequality in all cases. Okay, p equal 1 or infinity, and in this case we have two cases, this and arbitrary case. And we see this proposition too for any finite measure space X S mu. If we have this relation between P and Q, P is less than Q, then we have this inequality, so that LQ is a subset of LP, because if this be finite, then this is a finite number, so that if F belongs to LQ, F must belong to LP, and we see this in the previous step. Okay, and proposition for any mu and for any p belonging to this interval in LP of mu have this equal. Mr. Abdul Salam. Dear students, do you have my voice? For this equality, we see that if this norm equal to 0, then this must be equal to 0, because if this equal to 0, f must be 0 almost everywhere, so that all of these integrals equal to 0, and so this supremum equal to 0, and we have both sides of this equality equal to 0, so that in this case we have this equality. Thus we assume that this norm is non-zero. Okay? In this case, Holder inequality implies that for any h in L prime of mu with this relation, this integral is less than or equal this integral, and this by Holder inequality is less than or equal the p norm of f and p prime norm of h, and this is less than or equal p norm of f because we assume that this is less than or equal 1. Please note that supremum take on all h in L prime such that this norm is less than or equal 1, so that this is less than or equal p norm of f, and all of this is less than or equal this, so that this supremum must be less than or equal this. All of this object is less than or equal this fixed number. Okay, so that this supremum is less than this supremum is less than this. So we prove one side of this equality. If we prove opposite side, we prove this equality. Okay? To prove the inequality in the other direction, define h from x to f by this equality. H equal to the conjugate of f multiplied by f to the power of p minus 2 and divided by this norm. Then this integral equal to p norm of f. Okay, this integral equal to p norm of f, and this is easy because the integral of fh equal to the integral of f multiplied by this. This is our h, and we know that f multiplied by f bar equal to absolute value of f to the power of 2. Okay, we know that for any compound z bar equal to absolute value of z to the power of 2. Okay, we use this equality, and so this multiplication equal to f of x to the power of 2, and so all of this equal to this. f of x to the power of p minus 2 and f of x to the power of 2 equal to f of x to the power of p, and we have this multiplication or scalar so this is equal to, we repeat this 2 and this, okay, we can write this okay. We can write okay. This to the power of 2 multiplied by f of x to the power of p minus 2 d mu, okay, and this is equal to this integral, but this is equal to p norm of p to the power of p, okay, because we know that the integral, the p norm of f equal to this integral to the power of 1 divided by p, and so that we have this p norm must be powered by p, okay, p norm to the power of p, and so this fraction equal to p norm of f by this power p minus this, and this is equal to 1, this power equal to 1, so that this we have this equality, because we know that this summation equal to 1, so that if we multiply p to both sides of this equality, we see that 1 plus p divided by p prime equal to p, and so p minus this equal to 1, so that this is equal to 1, and we have this integral equal to p norm of f, this integral equal to p norm of f, and p prime norm of h equal to 1, because p prime norm of h equal to p prime norm of h equal to integral of h to the power of p prime d mu by this power, and this is equal to integral of all of this must be take to the power of p prime, okay, So we have this fraction f of x to the power of p prime this to the power of p prime then f of x to the power of p prime p minus 2 and this norm by this power to the power of p prime d mu. And we know that absolute value of z bar equal to absolute value of z, so that this is equal to absolute value of f. And finally all of this must be by this power, and so this is equal to this constant to the power of p and this integral. To p prime d mu of x. And this must be by this power and also this by p prime, okay. P prime, and this is by this power. And we see that this is equal to this norm by this power p divided by, let me write bigger, by this power p divided by p prime, and integral of f to the power of p d mu and this, because this equal to p you must check this, that is equal to P, okay? All of this, sorry, equal to P. And this is equal to this node, multiplied by this is this node, okay, and then we have this, let me write by parentheses, this power, and this is equal to this divided by this, P prime, P prime, and this node, and this is equal to 1. So this node equal to 1. Thus we have this equality 2 because we know that all of this integral must be less than this supremum, so that this integral must be less than this supremum, but this integral equal to this norm, so that the p norm of f must be less than this supremum, and we have this inequality 2. By these 2 we see that we have this equality, okay. And we prove this useful equality. Dear students, do you have any questions? Assume that P belongs to this interval. This case left as an excessor. Please solve this excessor. This is very easy. Okay. Inequality 7.5 implies that f plus g belongs to LP. I solve this for you. If f and g belong to LP, we have, okay, if f and g belong to LP, f plus c belong to LP, okay. Now suppose h belongs to LP prime and this norm is less than or equal 1, then this integral is less than or equal this integral, because we have triangle inequality, okay. We have triangle inequality. This is very trivial because this integral, okay, this integral f plus g multiplied by h okay is less than or equal this integral, sorry, is multiplied by h plus this multiplied by h, okay, and this is less than or equal by Holder inequality, both of this, okay. At the first is equal to this integral d mu plus this integral d mu, and in second this is less than or equal p norm of f multiplied by p prime norm of h, and this integral is less than or equal p norm of g, p norm of g multiplied by p prime norm of h, okay. So that we have this inequality, but we assume that this norm is less than or equal 1, so that this is less than or equal this. So we see that for any h, for any h, okay, for any h in LP prime of mu, if this norm is less than or equal 1, then this integral d mu is less than or equal this, so that the supremum of this is less than or equal this, but we know that by this proposition the supremum of this integral equal to the norm, okay. This, because we know that the integral of f plus g h d mu is less than or equal this, okay. Absolute value of it. H d mu, okay. So that this is less than this and this is less than this, and the supremum of this so this norm or this supremum this supremum H belong to L prime and this norm is less than or equal 1 must be less than this summation. P plus P norm of G. All of this is less than this, so that the supremum of this object must be less than this. But this supremum equal to this norm by this proposition 7.12. Okay. Okay. So we have this inequality, and this is Minkowski inequality. Okay. We continue in the next session. Dear students, do you have any question? Do you have any question? Okay, thank you very much and see you later, inshallah.